Greetings and welcome, ladies and gentlemen. We're talking about matrices yet again and expanding upon our understanding of them. Today we're going to talk about determinants, identities, and inverses of matrices. So up to this point, we know how to add and subtract. We know how to multiply by a scalar. And we also know how to multiply two matrices given they are of appropriate sizes with respect to each other. And we talked about how you can't really divide, but we're going to try to accomplish that today using inverses. So the first thing I want to talk about is some recall. And I'm going to talk about identities real quick of other, I guess we're going to talk just about numbers instead of matrices, just for quick recall, and figure out what is the additive identity. All right, so for identities, what could I add to a number? So x plus what, I'll call it capital I, would equal x. What is the additive identity? What would I equal? Yeah, so I equals 0. So 0 is referred to as the additive identity, right? For the operation of addition, you can add 0 to something, and it won't change it, right? How about multiplicative identity? Actually, I'll spell this out just because it's such a cool sounding word. Multiplicative identity. So x times I equals x. So what is the multiplicative identity? You got it. And let's see, I don't even know if this is a word, but I'm going to make it one. Exponentiation is the operation. So the exponentiative identity? That's excellent. So x to what power would equal x? Yeah, the first power, right? So that's the concept of an identity regarding some of our operations, at least with plain old real numbers, right? Let's talk about inverses. Now, the idea of an inverse is that it's kind of a set number, depending on the operation, that will give us back the identity. All right? So, for instance, the additive inverse if I want to figure out x plus, and I'm going to put x to the negative first power, raising something to the negative 1 is oftentimes a notation indicating inverse. So what could I add something? What would this x to the negative 1th power be? What would the inverse be? So if I have a number, what could I add to it that would give me the additive identity? So let's see, the additive identity was 0. So no. So what would the inverse be in this case? Yeah, it'd be negative x. It turns out for, I guess I'll just put it like that. For addition, the additive inverse is the opposite, is the word that I would use to describe that. So, opposite. Right? Let's see, how about multiplicative inverse? Let's see, so that would be x times x inverse gives us the multiplicative identity. What is the multiplicative identity again? 1. So what do I multiply something by? No. No. This?
Yeah, isn't x to the negative power negative, so when x the first x has to be...
Right, now I'm using this x to the negative 1 as just a notation to represent the idea of an inverse. But I'm thinking of, if I have the number 7, what would I multiply 7 by to get 1? If I have the number -20, what would I multiply that by to get 1? In this case, it's somewhat unique to every number, kind of like how the
I
opposite.
know what you're talking about, but I can't remember what it is.
2 times what is 1? Yeah. 10 times what is 1?
Whatever x's inverse is.
How would you describe that inverse?
1 over x.
1 over x, right? Exactly. And our mathy word for that is the reciprocal. Right? And remember, back in multiplication, right, the inverse operation of multiplication is division. And instead of dividing by something, we were also allowed to multiply by the reciprocal. And technically, if I was assuming this symbol and this to the negative first power meant what we typically assume it means, according to our properties of exponents, we actually would have moved this downstairs and given it a positive 1 exponent. So this is the most literal concept for this symbol right here. It would mean to reciprocate, right? Let's see, this one I don't even know. Let's see if we can figure out what this one would be. What is the exponentiative identity? Or inverse, sorry, my apologies. So let's see, what would that mean? That would mean x to what power is equal to 1. I don't even know if... Oh, wait. Oh, yeah. What was the exponentiative identity? It was 1. Anything to the 0th power is 1 is what you're saying? Yeah, so in this case, the inverse is the same in all cases. All right? So it's just, right, the 0th power, right, is our exponentiative inverse. So that's some basic concepts of identities and inverses. Okay, so an identity is basically some number that when using an operation, it will have no effect. We'll get back to our plain old spot, right? X was left unchanged. And our inverse uses the same operation, but combines with our number to give us our identity back. All right? So that's the idea there. So today what we're going to try to do is figure out, can we find out for matrices what is the multiplicative inverse and what is the multiplicative identity. Let's start with, now let's see, actually before I even talk about identities and multiplication, multiplicative identity for regular numbers, that's a terrible box. Man, that's the saddest box I've ever drawn, but that's okay. We've got was 1, right? Multiplying something by 1 left it unchanged. So let's talk about the inverse for, no, I'm sorry, the identity for matrices. So my question is, if I've got a 2 by 2 matrix, what could I multiply this by that would give me the same 2 by 2 matrix? Right? Well, what would it have to be? Well, I guess, okay, if it was a scalar, yes, you're absolutely right. But I'm trying to think of this identity is itself going to be a 2 by 2 matrix, because that's, right, the inner numbers would have to match, right, for multiplication. And then the outer numbers, I'd want it to give me back a 2 by 2, so it's giving me back the same matrix, right? Is what I'm looking for. So what would this identity matrix look like, do you think? What was the multiplicative identity for regular numbers? 1. So it's probably related to that. So you think just all ones? Negative ones. I'm looking for this matrix to be left unchanged. So if this was, for instance, x, well, I guess I'm going to run out of letters, w, x, y, z. I'm looking for this to still be w, x, y, z when it's all said and done. So, what's that? Yeah, some sort of ones in there would make sense, but let's see what would happen. Let's figure out what would our first row, first column answer be if this was all ones. So I'd multiply this. Right. So I'd have 1 times w is w, plus 1 times y is y. So I'd have w plus y would have been my first element instead of just w. What would I want to multiply y by in order to have that not count? I'd want that to be 0, right? So let's change this element to a 0. And then let's see. So 1 times w is w plus 0 times y is 0. So that gives me w. That works out. Aha. Let's see if this works for the next one. So multiplying first row, second column to give us the first row, second column, right? Let's see if this gives us just x. So 1 times x is x plus 0 times z is 0. So yeah, aha. So this, I think we've got our first row of the identity matrix. Let's see, second row, what's your guess? 0 and 1? You guys agree with your guess? It's probably ones and zeros. Could it be 1, 1, do you think? Yeah, because I'd have this times that, and I'd have w plus y again, except this time I just want the y, right? So the first one would have to be 0. I think 0, 1 is going to do it for us. Let's see, so yeah, so 0 w's plus 1 y is y, 0 x's plus 1 z is z. So I think this is our 2 by 2 identity matrix right there. So this is, what is the notation for that? My apologies. I believe I sub n. Aha. So I sub 2 is referring to a 2 by 2 identity matrix and is always going to look like that. It turns out I sub 3 would be a 3 by 3 identity matrix. These are always square matrices, by the way. And what's your guess for the first row of I sub 3? 1? 1, 0, 0, because I'd multiply it by my first thing and I wouldn't want the other two to affect it. What's your guess for the second row? Yep. And then the third row? You guys got it. So it turns out if you wanted to describe I sub n, some unknown sized matrix, all right, where I've got, some crazy number of rows and columns, right? It's still square. It turns out that for the identity matrix, it's essentially just going to be ones down the diagonal and zeros everywhere else. Okay? Is the idea. So I guess, yeah, I could put a little diagonal dot, dot, dot there. So it's all ones down the diagonal. And that's going to be our identity matrix. So I can multiply that by any matrix, and it's going to give me back the matrix that I had. So maybe that's not something to celebrate about. This is basically the lazy matrix is the identity. It's like I put it to work, but then it got nothing done at the end of the day. But this will be helpful for us because now that I know what the identity matrix is, I'm going to try to figure out the inverse. But I'm going to be kind to you guys. I'm not going to make you discover the inverse on your own. It looks like it would require solving I think a system of 4. Yeah. So I'm going to, in my kindness, help you out and just give it to you. But before that, I want to talk about a portion of the inverse. All right, there's kind of like 2 parts to the formula to get the inverse. And the first part is called the determinant. All right, so the first part is called the determinant. And it's kind of interesting. So let's see if I want, so here's matrix A, I'll say. And it's A, B, C, D. It's a 2 by 2 matrix. If I want to find the determinant of matrix A, there's a couple ways I can symbolize that. I might refer to it as this, where it looks like it's absolute value bars. All right, that means the determinant of matrix A. You can also write it this way, where you write DET parentheses A. That T is not an exponent. Let me actually make that look like more of a regular T. Determinant of matrix A. I also could write it this way, A, B, C, D, where I've just got kind of those absolute value-ish bars around the actual elements of the matrix with its size accordingly. So this is 3 ways of writing determinant, okay? So I want to point out that there's a huge difference between this and this, okay? This, with the little brackets, represents a matrix, all right? The determinant, we're going to find out, is equal to a single number, okay? This isn't a perfect analogy, but imagine if, if I talk about a square or a rectangle, you kind of have the idea of it as a shape. There's more complexity to it. But if I ask you what the area of that square or rectangle is, the area is just a single number that represents one feature of that shape. Okay, so the determinant is a single number that represents something valuable to us about the matrix. Okay, it's not really the area, though, just so you know. So it turns out the formula for the determinant, what I'm going to do is multiply what I'll call this primary diagonal. So I'll have A times D. And then I'll multiply this secondary diagonal, C times D. Sorry, C times B. My apologies, or B times C, whichever way you'd want to say that. And I'm going to subtract them. And that's our formula for a determinant of a 2 by 2 matrix. All right? So the yellow one I was referring to as the primary diagonal, but that is somewhat my own name for it. Right? So in the case of describing the identity, I could say that the primary diagonal is all 1s and all other elements are 0. Right? So with this little formula in hand, let's actually do some determinants of a 2 by 2. So I'm going to, do you guys have that written down yet? Okay, I'm going to scroll over, scroll up. Let's see. So let's see. I'll just say find the determinant. And just so you know, I often, because I happen to memorize things by first letter, I'll probably at some point in the next couple days, in referring to the determinant, I may say the word discriminant, which mathematically, do you guys remember what the discriminant was? No. Okay. The discriminant was the number under the radical in the quadratic formula, b squared minus 4ac, and it was used to determine the nature of the solutions of a quadratic equation. So anyways, I'll just happen to mix those words up sometimes. Let's see. So if I want to find the determinant of this 2 by 2 matrix, what I'm going to do is multiply this diagonal, -1 times 4. I'm going to write more work out just for the sake of our notes, but typically you'll be able to do that multiplication in your head. And then I'll multiply the secondary diagonal. 3 times 2. Right? And let's see, so that's going to be, I'm just going to go with one color from here on out. -4 minus 6, and I get a determinant of -10. Right, so not that bad. So let's try this matrix. I'll have you guys give that a try. So those of you watching the video, you can fast forward like 15 seconds if you want. Maybe 20. And we're back. So let's take a look at what we got here. So multiplying 3 times 4 is 12. -2 times -6. Oh man, I can't draw a good diagonal there. Is +12, right? Yep. And I subtract those, and I get 0. Now, a 0 in the determinant is going to give us an important fact about the inverse of the matrix. I'll give you that fact right now, in fact. Yes. Perfect. It turns out that any matrix whose determinant is 0 has no inverse. So in our case, determinants will allow us to do a little bit of a initial check to see if an inverse even exists for some of these matrices. Okay? Although the number, even when I get -10, that's still actually going to be valuable information to us because it'll be used in the calculation of the inverse matrix. Let's see. Let's do one more example of a determinant, but of a 3 by 3. And I'm going to do just one of these. And I'm going to use all my colors. 2, 1, 4. Let's do 3, -3, and 5. And let's do 7, 1, 9. Sure. Why not? So, let me show you how this is done. Alright, so the determinant of a 3 by 3. There's actually some other crazy methods out there. Your book will even have one. I'm not a fan of it. Your book does a 3 by 3 by having you find 3 separate 2 by 2 determinants within it and multiplying those by some other numbers and then adding and subtracting those all together. I feel like that's a little bit complicated. I mean, it's doable. It's just, but I like this method better. So for 3 by 3, what I'm going to do is take my first 2 columns and rewrite them just on the side with the same spacing that my other columns had. So it's not part of the matrix. I'm just using this for the sake of work. All right, so I rewrite those 2 columns. All right, and now I'm going to find the product of all of my downward diagonals. So let's see, 2 times -3 is -6, times 9 is what, -54, right? And now 1 times 5 times 7 is 35, I believe. So you see what I'm doing here? So this little yellow 7 came into play for this calculation. Technically, you could have also calculated that by being like this entered into a portal over here, Pac-Man style or asteroid style, and then like came out over here. But that's just weird, right? That's just weird. So that's 35. And let's see, my other diagonal is 4, 3, and 1, so that's 12. And I'm going to add those all together. Let's see. So that's going to be 47 and 54, so that's 3, 7. Negative 7, did I get that right? I hope so. So let's see. In trying to compare this concept to a 2 by 2 determinant, what do you think the next thing I'll do is? Yeah, we'll multiply our upwards diagonals. Exactly. So let's see, 7 times negative 3 is negative 21, times 4 is negative 84, I believe. Let me rewrite that, 8, that's a sloppy 8. And then 1 times 5 times 2 is 10. 9 times 3 times 1 is 27. And then I'll add those all together. So let's see, so that's 37, 84, 50. Is this negative 47? Let's see, negative 64, 44. Ooh. Let's see. Whew, I got it right. Okay. A little bit concerned. Now, what do you suspect will be our next move on this? What did we do with these numbers up here? Subtracting. So I'm going to take my primary diagonal sum and subtract my secondary diagonal sum. So I'm just going to write equals negative 7 minus a negative 47. That's going to be plus 47. So yeah, it looks like positive 40 is the determinant of this 3 by 3. Whew. Craziness. Now, I will expect you to know how to find the determinant of 2 by 2s and 3 by 3s. However, we're only going to find, by hand anyway, the inverses of 2 by 2s. Okay, so that will be nice. But I mean, it's really not that bad. It's the same. You see there's like a similar concept, and I'm sure if I gave you a 4 by 4, you'd be able to expand this strategy, you know, to a more, you know, it just kind of follows this pattern, this rhythm, you know, where you just rewrite probably 3 columns maybe for a 4 by 4 and go and then like add them all up and subtract them. Yeah, so it's not that bad. So let's see. So let's talk about inverses now. And we're specifically going to talk about inverses of a 2 by 2 matrix. So if I have matrix A being A, B, C, D again. Your book teaches the same concept, but they just label the little letters different, but it's the same exact pattern and formula. So the inverse of matrix A, denoted as A to the negative 1, so notice the similar concept there. The inverse of matrix A is going to be 1 over the determinant of A. So find the determinant. Notice there's the concept of a reciprocal right there even built within it. And I'm multiplying that by, get ready for this, my primary diagonal. I'm switching locations. So this is now D and A is my primary diagonal. And my secondary diagonal, I'm going to change the sign. So there's the oppositing effect, right, which is kind of what we saw in our additive identity, right, was the opposite. So I've got kind of concepts of reciprocality and oppositicality. I just made up those words. I think they sound great, though. But this is the idea of an inverse. Okay. So let's do an example. I'm just going to have time for one, I think. Ooh, wow. Yeah, this takes a little while to learn all these skills, but that's quite all right. Let's find the inverse of a matrix. Find A inverse. And so here's matrix A. It's going to be a 2 by 2, which is what we'd like. And let me actually just pick a nice little problem right here. I like it. 2, -3, and 4, 4. So, to find the inverse, what's the first thing you think we should do? Determinant. I knew what you meant, though. I know. Did I say discriminant at one point in this video already? I probably have at some point. So let's see. Let's first find the determinant. So let's see. 2 times 4 is 8. Minus 4 times -3, that's -12. So that is 20. Right? So step 1. Right? Find the determinant. Step 2. Now I can find the inverse. So it's going to be 1/20 multiplied by the matrix. And actually, up in my little formula, I might even draw these little arrows. So these guys switched locations, and these guys changed signs, right? Just so we super remember that. So let's see. So this is now the primary diagonal is going to be 4, 2. And the secondary diagonal is going to be -4 and +3, right? Now, sometimes your book might actually write its inverse out in this format and not multiply the scalar into it. And that's fine. Sometimes that will be good. But I actually want to multiply this out as well, just so you see it written as a matrix as well. So if I multiply all of these by 1/20, I will have 4 over 20, which reduces to, well, actually, even in that case, if you do distribute it in, and you're trying to find the whole inverse, I might recommend not simplifying those fractions. So you could possibly leave it as 4/20. And then we'd have 3/20. And then we'd have -4/20. And we would have 2/20. And I realize that most of those would simplify. But I kind of like that. That's going to be helpful in tomorrow's lesson when you'll start seeing the value of these inverses. Today we're just learning how to find them. But that would be cool to write your answer that way. And then if you really want to simplify it, that's the same as what? 1/5, 3/20, -1/5, and 1/10. Right? So I just want to point out that's what this inverse matrix looks like. So kind of crazy, not something you would expect. And actually what I want to do is a check, just so you kind of see how this all works out, is A times A inverse, well actually I'll even do it the other way, is A inverse times A equal to the identity? Let's see if that's true as a check. And I believe this actually even works if I do A times A inverse, if you're wondering. So let's see. So I'll have, I'm going to do it in this format right here, okay? Because this will be super friendly for us. So we'll have, I'm going to do the 1/20 at the very end. So I'll have 4, 3, -4, 2. So that's my A inverse. I'm multiplying that by matrix A, which is 2, -3, 4, 4. And we're going to multiply this out. What do I want this to equal when I'm all done? Speak up more confidently. 1? I just want it to equal some number 1. What was the identity for a 2 by 2 matrix?
1, 0,
1, 0, 0, 1. Exactly. So I'm expecting this to be a 2 by 2 matrix. That's 1, 0, 0, 1. So let's multiply this out. So I'm going to leave the 1/20th here until the very end. So it is going to be a 2 by 2. These can multiply. So let's do some row by column. And I'm going to do most of this work in my head here. So 4 times 2 is 8, right? Plus 3 times 4 is 12. So that's 20, right? Let's see, next one. 4 times negative 3 is negative 12. Plus 3 times 4 is 12. So negative 12 and 12 is 0. All right, this is looking good right now, I'm thinking. Let's see, second row, first column. Negative 4 times 2 is 8. Plus 2 times 4 is 8. That's 0. And let's see, negative 4 times negative 3 is 12. Plus 2 times 4 is 8. 12 plus 8 is 20. And I think you guys can see that when I multiply 1/20th by all of those, I do in fact get 1, 0, 0, 1. And I think that deserves a little bit of a exclamation mark. Wow, that's not factorial, by the way. I guess I should be careful. I'm going to make it like a fancy exclamation mark then. There we go. Like shock, surprise. Wow, who would have thought that multiplying, I mean, I saved the 1/20th till the end, but who would have thought that multiplying this by that would have come out so nicely, right? Like if I threw this problem at you when I first taught you how to multiply matrices, you guys would have been like, what? Fractions within multiplying matrices? But yeah, boy, it works out super nice, doesn't it? So we have, in fact, found the inverse. All right, so you could write it this way, or kind of like this way. This way is kind of okay too, but just be aware that different books might write their answers different ways. So well done, ladies and gentlemen. Well done. I think I'll just box this. There we go. A matrix inside of a box is like a box within a box. Good stuff. All right, friends. Bye-bye.